Hello, welcome. In this video, we're looking at what's called the Chord Chord power theorem. And I encourage you to pause the video and just read through it for yourself, and then press play and we'll talk about it together. Okay, so this theorem is saying that if you have two chords, so here's a chord, V to N is a chord. Chord goes from one side of a circle to the other without going through the middle. And over here, you have another chord, L and S. Another segment going from one side to another. Typically, I should say not through the middle, typically. And in this case, this theorem is telling us that if we take the product of the segments of one chord, so that would be this segment VE times this segment EN, so VE times EN, if we multiply those segments right there, that's going to actually equal the product of ES and, I'll put a circle here, LE. So I'm going to write that down. So VE times EN equals the product of LE times ES. And I try to label them all differently because we don't know if the segments are equal. We just know that their products end up being equal. So let's explain some of the logic of this. And like many things in geometry, we could tie it back to similarity or congruence of triangles in some way. And here we're going to focus on similarity. Let's think about this. First of all, we know that VEL is congruent, angle VEL is congruent to angle SEN. So VEL, that angle, is congruent to angle SEN. We know that because if you have vertical angles, then they are congruent. Vertical angles are always congruent. What else do we know? We know that, let's just draw a line from V to L, right here, and let's draw a line segment from S to N. While those segments are clearly different in length, we might notice this angle here is congruent to this angle here. All right, so I'm going to write that down and we'll talk about why that is. We know that LVE is congruent to angle NSE. NSE. And what's happening is here we have inscribed angles. So inscribed angles are angles that are on the circle, like this angle here is on the circle. These two inscribed angles share the same arc. If that happens, then they're congruent. Then they are congruent. So what do I mean share the same arc? Well, this arc right here, L all the way over to N, that arc is subtended by angle LVN, which means that the angle LVN, so this angle right here, basically spans the arc from one side to the other. Like if I was to draw the other segment there, you can see that it intercepts that arc. Well, the same is true for the angle NSL as well. This angle over here also intercepts the same arc, and since any arc is congruent to itself, those two angles are congruent to each other. And specifically, if we wanted to think about it, LVN is half the arc LN. Inscribed angles are half the arc. I'm going to write that on the side. We don't need it here, but also LVN is 1/2 arc LN. That's the relationship between the inscribed angle and the arc. So if this arc is, if this angle I would say is about 60 degrees, maybe the arc's about 120. Likewise, angle NSE is also half the same arc, and that's kind of the logic there. They're both half of the same arc, so they're equal to each other. Okay, what does that mean? That means we have two similar triangles. We have triangle VEL, I'll say it this way, V to E to L, is similar to triangle SEN. SEN. And that's by angle-angle similarity. The vertical angles are similar, and the vertical angles are congruent, and these inscribed angles are congruent as well. Okay, now we're almost done. Let's revisit this theorem. This theorem says that the product of the segments are equal to each other. How could that be? Well, this triangle VEL, I'm going to kind of draw it over here. Here's my estimation of VEL. V to E to L has this angle at LVE, and this angle here, one of the vertical angles, VEL. That is similar to this larger triangle. Let's try to sketch this out nicely. Don't want to zoom in, sorry. That rough sketch, I'm just redrawing this triangle here, okay? And that is S, E, and N. And we have those two angles congruent in these two. If you have two similar triangles, the ratio of their corresponding sides is proportional. So what we can say, like we're trying to prove the chord chord theorem, so I'm going to say VE, I can see that in the result we want to prove right there, the ratio of VE to LE, that ratio right there, is the same or equal, proportional to, the ratio of what? Well, it would be ES, this side right here, to EN right there, right? So whatever those side lengths are, they're proportional. So now we can write our proportion. So the ratio of VE to LE has to be equal to the ratio of ES to EN. And again, you have similar triangles. When you have similar triangles, then the corresponding sides are proportional. Corresponding sides are proportional. Okay, that's the reasoning right there. Finally, we can rearrange this to get what we want, which is up here. So here we can say that this product, VE times EN, is equal to this product, LE times ES. And one way we can explain why that is that the product of the means is equal to the product of the extremes, where the means is referring to these middle numbers here, and the extremes is referring to these numbers on the outside of the ratio here. So that is it. So I can say I proved it. Now I know the product of the means is equal to the product of the extremes. Right? So that's it. So that's the logic behind it, and other examples will use this chord power theorem a lot. Just remember, the products are equal because we have similar triangles, and the ratios of corresponding sides in similar triangles are equivalent. From there, we can figure this out, but the theorem gives us a little bit of a shortcut. All right, I hope this helped.